And with this, let us move on to our next keynote, which is going to be given by Professor Onur Mutlu. It's my great pleasure to announce him. He's currently a professor at the ETH in Zurich. He's also a faculty member at CMU, and besides, he has held various positions at Intel, AMD, VMware, or Google. He's a recipient of numerous, and I repeat, numerous awards from ACM, IEEE, NSF, Intel, CMU, and many others. And he's a holder of a large number of best paper awards and top picks and other recognitions. His current broad research interests are on computer architecture, systems, hardware security, and bioinformatics. He's best known for his work on commercial microprocessors and, of course, on memory and storage systems. We all remember his seminal papers on phase change memory architectures, STT-RAM, processing in memory, phenomena like row-clone, RowHammer, Ambit, Chipper, LazyPim, Conda, and so many others that simply cannot be listed here. With this, I'm truly delighted to give the virtual floor to Onur for his keynote, Memory-Centric Computing. With this, to you.
Thank you very much, Ilya. Can you hear me well? Okay, excellent. Yeah, it's a bit, thank you. It's a bit late here also. I'm on the Pacific time zone, but hopefully, hopefully everything will be okay. Okay. So thank you for the kind introduction. Thank you for inviting me to give this keynote talk also. I'm going to talk about memory-centric computing, which is going to synergize a lot with what Maya talked about. So let's jump in. So hopefully it's clear to everyone that computing is bottlenecked by data, and data is really key for many applications today and going forward. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And this needs to become more efficient in the future because data is increasing. We can generate more data than we can process, and we're doing increasingly more sophisticated things on the data. And you can see there are many, many interesting applications. Clearly, databases and data analytics is a key part of this conference. And data is a performance energy bottleneck, and memory and storage and networking becomes a huge bottleneck because of the growth in data in these workloads. But that's also true for the mobile end. These are some mobile workloads that are also interesting, and they're also bottlenecked by data in the end. And there are some emerging workloads like genome sequence analysis workloads that are going to be even more interesting going into the future. And here data is really growing explosively because the technologies that we use to generate this data are becoming better and better. As you can see, the cost of genome sequencing has been reducing exponentially much faster than the cost of a transistor has been reducing for more than a decade now, actually. And here, again, we have a problem because sequencing machines are extremely good at generating data. They're very specialized, whereas we're processing data using more general purpose machines that are really not a match to these sequencing machines. So going forward, we need to have a lot more specialization, in my opinion, so that we can take advantage of these sequencing machines to enable scientific discovery, as well as medical advancements, which we need going into the future. But this is a forward-looking application that we have been working on quite a bit for a decade or longer, actually. And I'll briefly mention that it's quite fascinating. And we have these devices that look like this, as you can see in this picture, and they're very good data generators, but unfortunately, they're terrible data analyzers. As a result, you need to move the data that's generated by these machines to the data centers all over the world. So you cause a lot of churn and have a huge impact on energy, sustainability, etc., just to be able to process the data that's really important to process from these machines. And if you're really interested in this topic, we've written a bunch of articles, scientific articles, as well as some overview articles like this. I'm not going to talk a lot more about this, but I will mention this paper later on, where we actually accelerate genome analysis using FPGA-based near memory architectures as well. And we have more specialized architectures to do approximate string matching, as you can see over here, and to do filtering in the storage system also. This appeared at ASPLOS just a couple of months ago. And the future of genome sequencing and analysis is very bright, I think, but we need to really process the data where it makes sense, meaning where it's generated without moving it a lot. And this actually enables a lot of interesting analyses, very quick analyses, for example, that you can give these devices to the doctors or the patients or people so that they can do these sequence analysis themselves in a private manner without moving the data to a lot. Okay, as I said, I'm not going to talk about this a lot, but you can find a lot more information on our talks as well as lectures online. Okay, so this was a particular example, but many applications today have deal with a lot of data, and data overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability in the end. It greatly impacts robustness, energy, performance, cost, and security as well. And if you go back to the fundamentals, a computing system has three key components: computation, communication, storage, and memory. And we've been heavily optimizing the computing unit a lot. And we have not paying enough attention to making the communication and memory and storage units, other parts of the system, intelligent, let's say. Basically, we're very processor-centric. And as a result, we have heavily optimized the processing units. And if you look at the processing units, even the processor chip most of it is dedicated to storing and moving data. We have levels and levels of caches, interconnects, memory controllers, other caches outside the chip, and other interconnects, other storage. And if you look at a particular node, more than 90% of the node is dedicated to storing and moving data. Yet, the system is still bottlenecked by memory. Basically, we're dedicating all these resources, we're still bottlenecked by memory. This should immediately tell us that we're doing something wrong in our systems. And I think we really need to take a step back and start doing something right in our systems, if not for performance, for definitely energy efficiency and sustainability going into the future. And as a result, we have numbers that look like this. This is a study that we did with Google a few years ago, where we found out that more than 60% of the total system energy is spent on data movement on mobile workloads that I showed you in the prior slide. I'm going to get back to this later on. Okay, so basically my axiom in this talk is going to be that an intelligent architecture needs to handle data well. And we want intelligent architectures that can process data intelligently, because these intelligent architectures will be everywhere in our lives, making decisions for us. We don't want non-intelligent architectures making decisions for us going into the future. So how do we handle that data well? So I believe there are three components to this. I'm going to focus especially on the first one. Before we go into it, the first one, we need to ensure that data doesn't overwhelm the components. Yeah, intelligent algorithms, intelligent architectures, we have whole system designs, algorithms, architectures, devices, and we're going to talk a lot about this one. But we also want to take advantage of vast amounts of data and metadata that's flowing through the system. Today, we're actually wasting a lot of opportunity because our systems cannot self-optimize themselves, meaning, for example, improve the decisions that are made in the memory controller, caches, etc., in a fundamentally better way, so that they can design their own policies dynamically, adapt their own policies. Basically, we're talking about self-learning systems by adapting to the data. This is also important. These are data-driven systems as opposed to human-driven systems. Today's systems are very human-driven. Humans make the policy decisions, not the machines themselves. I think we need to think about that, but I don't have time to talk about this much. I will briefly mention it again. And the third important thing is we need to understand exploit properties of different data, and data has many, many different properties. Today, we're not exposing them to the underlying architecture as much. It gets not even expressed at the semantic level, at the higher levels, like software levels. For example, we have privacy properties, security properties, compressibility properties, approximability properties, even performance properties like locality properties. Even those do not get expressed very well at the higher levels, let alone communicated down to the architecture. I think we should be expressing them and communicating them to the underlying architecture so that architectures and algorithms can make better decisions going into the future. So I think this brings me to three corollaries that I kind of talked about. Today's architectures are very processor-centric. We need to make them data-centric, and we're going to spend a lot of time in this talk talking about this one. Today's architectures make very simple human-driven decisions, and we need to change them to make more data-driven decisions, become more self-optimizing. And today's architectures do not know enough about the data because that characteristics of different data do not get expressed. Different characteristics of different data do not get expressed. As a result, they usually treat data all the same. As a result, they make component-aware decisions. For example, if we take the example of a memory controller, Memory controller doesn't say, oh, this data is very security critical, or this data is very performance critical. Let me handle it differently. It basically says, oh, I have this bank and I have this row buffer in memory, and I have these other requests. I'm going to try to schedule things such that I can maximize the performance of my component, as opposed to data aware decisions that is data criticality aware, let's say. So again, I think these three things are together constitute a much more intelligent system, but we're going to focus on the data-centric part and not talk enough about the data-driven and data-aware part because we don't have time in this short keynote today. But if you're interested, I'll mention some talks. But to be able to do this, I think we need to revisit the entire stack. We cannot just do it at one level of the stack. We really need to cut through from algorithms all the way to devices. And sometimes design the algorithm, redesign the algorithms for the devices, and sometimes design the devices for the algorithms, sometimes, and hopefully, more importantly, co-design everything across the stack. Of course, this may sound like a daunting task, and it is a daunting task if you want to do it completely like that, but I believe we can get there step by step. And I'm going to give you examples of some, let's say, simple steps that can buy significant performance energy improvements in today's systems. So, okay, this is what I said earlier, but basically, if you would like to get the highest energy efficiency and performance, as well as other characteristics like reliability, security, etc., we really need to co-design across the hierarchy and specialize as much as possible. So that leads us to data-centric, data-driven, and data-aware architectures. And in this short paper, we discuss properties of these architectures. If you're interested, you can take a look at it, and also the longer video that I mentioned over here. Okay, so let me now focus on the data-centric part. I will have a lot of slides. I'm going to skip a lot of them, frankly, but they're there for really reference. These will all be made available. I'm going to mention just the key points in many of the slides. So this is data-centric or memory-centric architectures, whatever you would like to call it. I believe even this one has multiple properties. Basically, if we want to be data-centric, we really want to process data where it resides, where it makes sense, while it's moving. And we should really enable that capability of processing data everywhere possible, not just the processor or the accelerators as we do it today, but also the storage system, also the sensors, also the network, main memory, which we'll focus a lot on, caches, as well as scratch pads, registers, basically wherever data resides. On top of this, I think we really need to have low latency and low energy data access. This is an orthogonal thing that is important. We really want to reduce the latency and energy of data access, which I'm not going to talk about. And there's a lot of interesting research going on in this direction as well. We want to make data storage and processing much more low cost. And there's also a lot of interesting research going on here. And we want to have intelligent controllers managing data intelligently, handling robustness, security, cost, and performance. Again, these three I'm not going to talk about. I'm going to focus on the first one, which is processing data where it makes sense. And this is not a new idea, basically. This is an old idea. More than 60 years ago, people have actually looked at processing in or near memory. They called it logic in memory at that time. And people have looked at it for decades and decades. And this is a nice paper by Harold Stone in 1970, as you can see. Why is it more interesting today? And why is it happening today, actually? I will show that it's happening today, actually, by major companies. But there are two major reasons, basically. I think we're being pushed by technology to the limits today. As a result, technology scaling is at jeopardy. DRAM, for example, which is the main memory used for essentially all devices that we have today, is not scaling very well. And we're having a lot of issues. I'm going to talk about that very briefly. As a result, industry is examining controllers close to DRAM, and industry is much more open to new memory architectures today than it used to be. And you can see some of these new architectures that were developed based on some timeline. Hybrid Memory Cube was one example. 3D stack memories in general is one example. This is an early prototype by Micron, as you can see over here. And more recently, the UpMem company introduced processing near memory architectures. Samsung and more recently SK Hynix also introduced these near bank architectures, as we will discuss. And there are other forms of near DRAM chip architectures where you can actually do the processing as well. And part of the reason why this is happening is because technology scaling is not going well. And we knew that this is a problem, basically. For a long time, technology scaling, DRAM technology was not scaling very well. And this is one paper that we had written about a decade ago, let's say, And we argued that memory needs to be much more intelligent to overcome some of these scaling issues. And this is one example that we studied with Facebook. Basically, we analyzed all of the memory areas that they have in their servers. And the key result is depicted in this figure, which shows that the server failure rate heavily correlates with the density of the memory chip that's employed in the server. As chips get denser, server failure rate increases because you get more memory areas essentially. Why? Because in denser chips, you pack a lot more cells, a lot more DRAM cells in a given millimeter square, and cells are smaller, and cells are much more vulnerable to noise because they're much closer to each other. So these are example scaling issues. And another example scaling issue is RowHammer that was mentioned in the introduction. And this is basically the fact that today you can predictably induce errors in most DRAM memory chips. Clearly, this should not be happening. You should not be able to induce any error in any chip, let alone do it predictably. Soft errors happen, but they happen once in a while. Here, you can actually manipulate the access patterns to actually to cause errors. And I'm not going to talk about this in detail, but this is a reliability problem as well as a security problem because someone can take over your system, or they cause data corruption, or break confidentiality if they can induce these bit flips. And I'll refer you to some other talks that we have delivered and some other papers that we have written on this topic. This covers actually an across the stack memory survey of RowHammer until 2019. But a lot of interesting things happened in RowHammer in 2020 and beyond as well. But if you want to know about some of those really interesting things that happened in the RowHammer research or DRAM scaling, DRAM security research, I would refer you to this relatively short talk that I delivered at ASPLOS very recently also. Okay, those are some scaling issues. Another scaling issue is hybrid memory. Essentially, hybrid memory enables better scaling because it mixes multiple different technologies or multiple different incarnations of the same technology, like multiple different DRAM technologies. But DRAM and phase change memory is another example. And you could actually scale memory much better this way by putting together these different technologies that have different characteristics. And the hardware and software manage data allocation and movement to achieve the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. But of course, to be able to do this, you really need to have an intelligent controller and across the stack design where this controller is aware of the application characteristics as well as the device characteristics. So I think hybrid memory is another example where we really need intelligence. And it's another example of the scaling issue. So that brings me to the point over here, which is that main memory needs intelligent controllers for scaling. And RowHammer is sold by intelligent controllers. I'm not going to talk about the solutions, but you can find information about it. And industry is interestingly writing papers about it too. This is a paper that was written by Samsung and Intel in 2014. These two companies don't normally talk to each other, but because of the DRAM scaling issues, they argued that controllers need to be intelligent. And I refer you to that paper. And intelligent controllers actually enable very, very interesting things. This is a recent paper that we published at Micro that shows that if you have an intelligent controller that understands what's going on in the error characteristics of the DRAM chip, you can identify uncorrectable errors and you can also correct them actually. And again, I'll refer you to the papers. So basically the takeaway is that intelligent memory controllers can avoid many failures and enable much better technology scaling. And that's why we're seeing increasingly more companies putting intelligence into the memory controllers to solve RowHammer, to add error correction, etc., and also to add computation, as we will see soon. Okay, so that was the push from technology part. There's a big pull from systems and applications that's equally and even more important potentially. That's basically pulling us to do something different in our systems, basically to be more memory-centric. And this can be summarized in three things, basically. Today, data access is a major bottleneck, as we discussed. Energy consumption is a key limiter, and data movement energy dominates compute. And this has been like this for a while, but it's becoming much worse, basically. And the key question is, do we want a world that looks like this or like this? I would argue that we want high performance, energy efficiency, and sustainability all at the same time. We don't want to give up any of these, in my opinion, because clearly we can get energy efficiency and sustainability by giving up high performance, but that may not be good for solving the complex problems that we have into the future. And the key realization is that data access is the major performance energy bottleneck today. And our current design principles cause great energy waste, as well as great performance loss. Basically, because processing of data is performed far away from the data, we're causing a lot of energy waste. We're causing a lot of performance loss. To overcome the performance loss, we actually make our systems a lot more complicated, add many, many levels of cache hierarchies, many massive levels of multi-threading, let's say, prefetching, out-of-order execution at both software and hardware levels. As a result, systems are becoming much more complex and energy waste is actually compounding. When these techniques that we add work, they're not bad, but usually they don't work perfectly. And sometimes they don't work at all almost. If you have random access applications that are increasingly interesting today, for example, these techniques do not work. As a result, we're wasting even more energy while getting not enough performance from these techniques. So in order to get rid of this vicious cycle, I think we need to really get to the bottom of the problem, which is the fact that today's computing systems are extremely processor-centric. All data is processed in the processor at great system cost, and data storage units and everything else in the system is relatively dumb, let's say. They're largely unoptimized. Yet we know that memory is a big bottleneck. This is actually, but it's becoming bigger, basically. This is a quote from Dick Seitz, who was the chief architect of alpha processors in the 1990s. He basically wrote a one-pager article that was titled, "Is the Memory Stupid?" in 1990s, where he basically said, we built this alpha processor that is able to finish 4 instructions per cycle, but on these important database workloads, it's finishing 1 instruction every 4.7 cycles. Why? It's waiting for memory. And he basically ends the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And fast forward about 10 years, we did a study with Intel for my PhD thesis, and we showed basically that the processors that are designed at that time by Intel on the applications that were designed for are essentially waiting for main memory most of the time. And if you're interested, you can read the papers related to that. And more recently, Google has done a similar study on their own workloads, according to them, all of their data center workloads, where they showed essentially the same thing. Most of the time, the processor is waiting for memory. Very little amount of the time, the processor is doing useful work. And by looking at this picture, we should probably be saying, is this the right way of designing our systems? And I would argue that no. Why? Because we're very processor-centric. As a result, the system is grossly imbalanced. Almost everything stores and moves data, except for the computation units that are actually a very small fraction of the system. And we also have an overly complex and bloated processor to tolerate the data movement. This is true for accelerators as well. As a result, we're basically increasing energy inefficiency. We're low performance because we could have used those resources somewhere else, and we're very complex. So basically, processor-centric design is making our systems a lot more complex than they need to be and a lot more energy efficient than they really need to be. And even though most of the system is dedicated to storing and moving data, we're still bottlenecked by memory. So we're back to the picture that I showed you earlier. So that was the performance perspective. Energy perspective is actually even worse. If you look at the energy of different operations, a complicated arithmetic operation today is very cheap due to the technology scaling that we have seen in CMOS and Moore's law, essentially. But a memory access is very expensive. And the difference is between 2 to 3 orders of magnitude. Basically, we don't want to move data, essentially. And there are a lot of papers studying that. And our paper with Google is one example where it shows that more than 60% of the total system energy is spent only on data movement across the memory hierarchy. Okay. So basically, I would argue that we do not want to move data in our systems. We really need to have a paradigm shift to enable computation with minimal data movement, compute where it makes sense, and make computing architectures more data-centric. And that brings us to processing inside memory, but also inside storage, also inside the network, also inside the tape, if you can do that, inside the cache, essentially everywhere. I'm going to focus more on processing inside the main memory going forward, because main memory has a very special place today. It's very large, it's growing, and a lot of applications take advantage of that large, reasonably low latency access. So it has a nice place. I would argue that storage also has a nice place, but main memory's latency properties are even better than storage. So even though I think data-centric computing should be done everywhere, memory may be the difficult place to enable it because of the interfaces that we have also. So basically, we would like to store our applications in memory, and we would like to be able to query memory saying, memory, can you execute this function for me on these applications, let's say on this application, and memory returns the results. This sounds great, of course, but there are many, many challenges. And there are many questions. I'm not going to answer all of them, but I'm going to give you examples in the remaining part of the talk. How do we design the compute-capable memory and the controllers? How do we design the communication units and processors, software and hardware interfaces, system software compilers and languages, and algorithms and theoretical foundations as well? Again, this brings us to the picture that I showed you earlier. This is an across-the-stack problem. We really need to co-design across the hierarchy. At some point, we really need to rethink the theoretical foundations of computing as well, because today's theoretical foundations of computing are very processor-centric as well. We're counting operations to quantify the complexity of algorithms, but that may not be that interesting or important if data movement is the big bottleneck that we have. We should probably have a start developing a more data-centric theory of computing as well going into the future. I'm going to cover some things from this paper that we have recently released. We're going to update it actually by the end of this month also. That talks about a lot of issues in modern processing in memory. If you're interested, I'd refer you to that paper for a lot more than what I can cover in the remaining part of this keynote. And basically, we talk about a lot of adoption issues over here also. So processing in memory is not a new idea, as I said, but we need to think differently from past approaches going forward. I'm going to cover two different approaches and different thinking in both approaches, hopefully. We want to take advantage of existing technologies, new technologies also, and we want to make sure, we want to basically devise techniques such that processing using memory or near memory happens. So what's the difference between using and near memory? Let me cover near memory quickly. Near memory is very similar to today's paradigm. Today, processor is here, memory is here. They're far away from each other. Processing near memory says, put the processor closer to memory. And at some point, processor comes very close to memory, meaning next to a bank, for example. But it's still programmed very similarly. It's still a von Neumann processor, let's say. So the programming model doesn't change, but it's much, much closer to memory. Processing using memory is fundamentally different. Here, we're going to take advantage of the memory array. We have memory, and inside memory, we have cells. These cells, we've been using it for storage, but let's use it, and cells and arrays, but let's use it for computation as well. These have capability, especially analog computation capability or data transfer capability. And the idea is to exploit this capability so that we can do computation as well as memory in the same cells. So this is fundamentally different than what we do today, clearly. And this leads us to new models as well. But you could also augment today's models using processing using memory, as I will mention soon. And our paper covers a lot more of these approaches. Okay, so let's jump into processing using memory first. The basic idea is to take advantage of operational principles of memory to perform bulk data movement and computation inside memory. I'll show you we can exploit internal connectivity to move data, but we can also exploit analog computation capability. And who knows what else if we can actually slightly modify the memory circuitry to do these more robustly and also more powerfully, let's say. So I'm going to give you some examples. And initially, I will start by cheating, let's say, but cheating it's not cheating because data copy and initialization happens a lot in our real systems, databases, for example. If you imagine you're initializing a 1 terabyte database, physically initializing this takes time. And recently, Google, in their paper, ISCA 2015 paper, showed that just 2 system calls, memmove and memcopy, that do copying of data, consume 5% of the execution cycles in their data center, essentially across all of their workloads. And that's a big number, basically, across a lot of workloads. So how do we do memory copy today? Basically, we have to go through the processor because we're processor-centric. But why don't we do it in memory? Basically, tell the memory, please do this copy for me and don't disturb anything else in the system. This would be great because this is low latency. You could exploit internal connectivity, low bandwidth utilization, and actually no data bus bandwidth utilized on the most important, let's say, bandwidth bottleneck resource, which is the memory bus. No cache pollution, but you could eliminate that by doing this through the DMA engine today. And no unwanted data movement, essentially. And I'm going to show you a mechanism very quickly that takes a 4 kilobyte page copy from 1,000 nanoseconds to about 90 nanoseconds, and that reduces the energy significantly as well. And the idea is very simple. This is the fastest way you can build in DRAM as we know it today. We call it row clone. There are other components to it, but I'm going to ignore the bank-to-bank components, for example. Assume that 2 pages reside in the same DRAM subarray that shares sense amplifiers, which is a row buffer. The idea is very simple, basically. You first activate the first row, which brings the data into the sense amplifiers, and then you activate the destination row, which implicitly deactivates the source row, but its data stays in the row buffer. And when you activate the destination row, the data in the row buffer gets copied into the destination row. So by doing 2 consecutive activates, you can copy a row of data internally in DRAM. And this is negligible hardware cost if you want to do it, let's say, robustly. But in existing DRAM chips, you can actually do it. I'm going to mention a paper where we have released where you can actually do this in existing DRAM chips by violating the timing parameters in DRAM chips by, that govern activate to activate delays, for example. So it's fascinating that existing DRAM chips can robustly or reasonably robustly support it without any changes today. This shows that existing DRAM chips are actually capable of doing this data movement and also a computation, as we will see later. But basically, if you do this, you get significant performance improvements in 4 kilobyte page copy and energy improvements also. And applications also improve, but I'll refer you to the paper later. But clearly, data doesn't reside inside the subarrays. You can change the system such that most of your data copies are inside the subarrays. That's the algorithm architecture co-design now. But you cannot do it all in all cases. So you really need to have movement support between different banks as well as between different subarrays, which we have tackled in our future work, which I'm not going to talk about, but I'll refer you to one of the lectures over here. This is the original row clone paper. And this is the paper that I mentioned where based on some other prior work that was done by others, we showed that you can actually do this in real DRAM chips. And you can actually, we release this infrastructure so you can try it out for yourself to see the effect of doing this in real DRAM chips. Of course, you need to do it with an FPGA platform today because existing memory controllers don't support this sort of consecutive activates to be done faster. Okay, and if there's a lot more to cover actually in row clone and processing using DRAM, I'll refer you to this paper. But I will this talk from our lectures. But the mindset is actually we would like to use memory as an accelerator. We'd like to use memory as an accelerator for the task it's really good at, and copying data is one of those tasks. We're building accelerators all over the place, except they're all sitting on the left side of the memory bus. Why don't we put some accelerators on the right side of the memory bus that are not bottlenecked by memory? And that's the idea. And programming of this can be more similar to a conventional accelerator, but we will talk about that in a little bit. So this was maybe cheating. We can actually do in-memory computation as well. Basically, at low cost, without modifying the DRAM too much, we can exploit its analog computation capability. And the key idea is activating multiple rows perform computation, in particular majority computation, and you get significant performance energy improvements. I'm going to mention this quickly. New memory technologies enable even more opportunities. These emerging memory technologies like phase change memory, memristors, RRAM, STT-MRAM, they all have the property of operating on data with minimal movement. They also have the ability to actually do matrix vector multiplication due to their crossbar array designs. That's different from DRAM. And also, they also have the ability to do M-bit-like computation, which I'm going to describe as other works have shown. So basically, new memory technologies are very interesting because they're non-volatile, but they're not there yet. I believe they're going to be there in the future. So we should really explore both DRAM as well as emerging memory technologies for in-memory computation. Let me give you the basic idea of triple row activation in DRAM. Idea is very simple, actually. If you activate 3 rows in DRAM, here I'm showing you 1 cell in each row, but imagine 8 kilobytes or 16 kilobytes, depending on the configuration. You can do this operation on 8 kilobytes of data, and you can do this operation on thousands of subarrays, let's say, so millions of bits, basically. And the idea is if you activate 3 rows, these 3 cells share their charge together, and based on charge sharing principles, the output is a bitwise majority function, based on circuit level principles, essentially. And basically, you can do bitwise majority computation across millions of cells. This is great. Majority function is nice, but you can re-express the Boolean equation like this, and you can now control C. If C is 1, you get the OR of A and B. If C is 0, you get the end of A and B. Now you can have OR and AND. Now we actually later showed that you can actually, with a little bit more cost, you can have the complement of the data as well, because if you look at this picture, the complement exists on the other side of the sense amplifier. You just need to feed it back into the array. So this requires a little bit more cost, but you can also do not. Basically, you can have a functionally complete bitwise execution system inside DRAM. And this is also validated in real DRAM chips. Real DRAM chips, even though they're not designed for this, real DRAM chips have some capability to actually perform this if you violate the timing parameters. But this is not robustly done, clearly, because real DRAM chips are not designed for this purpose today. So you will need to violate the timing parameters in a very careful way. But you can actually show it in real DRAM chips. Okay, what does this enable? Basically, if your workloads can be rewritten or already written to maximize bulk bitwise operations, you can get significant performance improvements. Bitweaving database is one of the first things that we experimented with, for example. Bitfunnel web search engine is another thing that we experimented with, bitmap indices, etc. So there are a bunch of workloads that are already written to perform bulk bitwise operations, and their adaptation to this system doesn't take a lot of effort, as we have done. And this is one example from basically Bitweaving database. We showed basically that you can greatly reduce the latencies of the queries by using Ambit. There are more results in the paper that I'm not going to talk about, but you can take a look at the paper and the papers that build on it. So making this programmable is also important, and making this generalizable to other operations is important. And recently we have released the SimDRAM framework. The basic idea here is it's essentially a framework. User can put any desired operation it can be very complex operation, like a convolution, for example. And using CAD algorithms, computer-aided design algorithms, we basically turn this into majority not implementation. And these get expressed as DRAM commands. And basically a single instruction, a convolution, for example, gets stored as a microprogram that is executed by the memory controller. Essentially, this microprogram is executed by the memory controller. And whenever the user invokes an instruction, let's say, that microprogram gets invoked in the memory controller. And this sort of bulk bitwise execution happens. And the results essentially gets communicated back to the program. So this is one way of integrating this bulk bitwise execution paradigm into existing programs by using instructions or processing in memory enabled instructions, if you will. And with this framework, we showed that you can get significant performance improvements over CPUs and high-end GPUs, as well as energy efficiency improvements. And again, I will refer you to the paper for more details of this. So there's a lot more to talk about in processing using memory, but we don't have time. You can actually have physical unclonable functions, security functions. You can generate truly random numbers using the properties of DRAM. And we have a bunch of papers on that, but I don't have time to talk about. Basically, you can build a security infrastructure on the DRAM side as well. Okay, now in the remaining time, let me talk about processing near memory as well as adoption issues and real processing in memory systems, and then we will conclude. So processing near memory, as I said, is similar to today's systems, except you put processors close to memory or inside the memory chip. And here, what becomes interesting is specialization, basically. Can you specialize the system for interesting applications like graph processing? This is one of the first things that we tackled when we were looking at processing near memory. And graph processing is interesting because you get a lot of random memory accesses with little amount of computation. So it's very much memory bottleneck. And we wanted to solve this memory bottleneck by processing inside the logic layer of 3D stacked memories. 3D stacked memories have logic layer as well as memory layers. And you can put processors inside the logic layer such that they can have low latency, high bandwidth, low energy access to the memory layers. And you can connect these cubes, if you will, to each other to scale the system. And other two monolithic three-dimensional systems are under development, and they're very, very interesting, which I don't have time to talk about. But this was a system we designed for graph analytics. Basically, we start with this 3D cube, if you will. Inside the logic layer, we have a bunch of in-order cores, as you can see over here, and also DRAM controllers. And these communicate with each other through an interconnection network. And to scale up the system for large graphs, of course, you need to connect these cubes to each other. And at the system level, this accelerator is essentially like a GPU or primitive GPU, if you will. It's connected to a host processor using a memory mapped interface. It's non-cacheable, physically addressed. There's no virtual memory inside it. Essentially, the processor offloads the graph computation onto this accelerator, and the graph computation happens on this accelerator. And the accelerator is programmed using message passing. It's essentially like a distributed system. The processors send messages to each other. They basically send function calls to each other. They don't move the data. They basically send operations to the data. So the data that whenever you want to update a node, for example, a graph nodes get partitioned on these cubes, as well as within the vaults, let's say, inside the cube. These are called vaults. And whenever you want to update a graph node, you send a message to the node that hosts the graph node. And you can think of this as a distributed system, essentially. And this reduces data movement significantly, assuming your graph is partitioned reasonably. And there are a lot of later works that show that you can partition your graph even better than what we did in this initial work and get a lot better performance. And we have some prefetching mechanisms that are also interesting that I'm not going to talk about. Let me give you some results on the system. At the time we developed the system. Of course, this is all in simulation because we didn't have infrastructure at that point. Tesseract doesn't look like any of the systems that were there because it's not processor-centric. All of the other systems are processor-centric. As a result, the memory bandwidth is bottlenecked. Whereas Tesseract is memory-centric. You can see that memory and processors are combined, and you get significantly high memory bandwidth for 512 processors over here. And the performance improvements are commensurate on average across 5 different graph processing algorithms. You get more than 13x performance improvement. Later works actually improved a lot of the algorithms that we started out with, like graph partitioning, as I said, like balancing, interrupt handling, etc. So later works show that you can actually get to 2 orders of magnitude. And energy reduction that we showed was about 8x, let's say, on average. And later works actually show that you can do much better, close to 2 orders of magnitude again. So this is an initial example of how near memory processing can actually improve performance and energy significantly. Later, we actually did other works to enable this to become better. We worked with Google, for example, to show that you could actually get significant benefits in consumer devices, and consumer devices are extremely energy bottleneck. We analyzed these 4 workloads, as I mentioned, and I gave you already this result. Basically, on these 4 workloads, a mobile system spends more than 60% of its energy on data movement. And we would like to overcome this data movement bottleneck by putting processing inside the memory again, near memory. The challenge here is a very limited energy and area budget, and we discussed this challenge a lot more in the paper. But what enables us to overcome this challenge is that in a lot of these workloads, data movement often comes from very simple functions. So we can actually implement lightweight logic to implement these simple functions inside the memory, like in small embedded low power cores or small fixed function accelerators or small reconfigurable accelerators. I believe actually the in-memory accelerators also need to be heterogeneous going into the future. And we showed that offloading to this PIM logic, simple functions, not rewriting your entire program like we did in graph analytics, but just offloading simple functions can buy you 2.3x and 2.2x performance improvement, which is significant. And it can be improved over time by better offloading, let's say. Okay, I will not go into the workload analysis more detail, but this is one example from TensorFlow, for example, that shows that you get significant data movement bottlenecks, and data movement bottlenecks often comes from 2 major functions in this particular case. If you're interested, there's a lot more data in this paper. So I can refer you to many other papers. I'm not going to go through each of them, but we can do near memory processing with GPUs. You can have GPUs, simple GPUs in the logic layer, and it can augment the processing of a main GPU. So data-centric or data bottleneck computations can be offloaded to this simpler GPU in the memory layers. And we did that transparently using compiler support, and we gained significant performance improvements in this work that we did together with NVIDIA, for example. There's also other things that you can do by scheduling GPU kernels in intelligent ways. You can accelerate linked data structures by reducing their latency, and memory traversals can happen also in near memory engines. Dependent cache misses are another example. We did that both transparently as well as by exporting it to the programmer. You can accelerate prefetching mechanisms. You can accelerate climate modeling using existing near memory processing units in FPGAs. I will briefly mention this if you have time later on. You can accelerate approximate string matching. And more recently, this is a work that's going to appear at ISCA soon. We showed that you can accelerate sequence to graph mapping also significantly in genome analysis. You can accelerate time series analysis. So there are a lot of interesting applications that are data bottleneck, as I mentioned, and they're very nice case studies that show that by algorithm architecture co-design, you can improve performance as well as energy at the same time. Graph pattern mining is another one. And in this ICDE conference, we have a paper that talks about accelerating HTAP database systems by co-designing, again, algorithms and architectures with some data-centric accelerators. I'll refer you to Geraldo's talk that's going to happen soon. I will mention neural network inference briefly because this is very interesting, I think. We did another work with Google that was published last year at PACT, where we looked at neural networks that are used at Google. And this is a busy slide, but basically the takeaway is that there's no one-size-fits-all accelerator for neural networks, even though today's accelerators are very monolithic. We really want to design accelerators that can fit the characteristics of different layers in a neural network as well as different models. And if you classify the different layers and different models, some of them are very processor bound, many of them are actually very, let's say, memory bound. And for those memory bound parts of the neural network layers as well as models, you will need data-centric accelerators, near memory accelerators, basically. So if you have 3 accelerators, for example, that are specifically designed for these Google Edge models, you can improve both performance and energy by more than 3x, as you can see over here, while also reducing the area that you dedicate to the accelerator. So basically, you win on performance, efficiency, energy efficiency, as well as area. So that's the benefit of actually hardware algorithm co-design that is specialized for systems applications, as you can see. Okay, there are more slides over here, but I'll go through these relatively quickly. These basically show that these different models, neural network models that are proprietary at Google, have very different characteristics. Some of them are extremely memory intensive, as you can see. Some of them are not so memory intensive. So why don't we design accelerators that are more fit for families of these models as well as layers? And you get significant performance energy improvements. I'll refer you to the paper. You can also do real system works today using FPGAs that have high bandwidth memory. And we did this together with IBM. Basically, we looked at 2 workloads, weather modeling and genome analysis, and 2 different technologies, DDR4 and HBM technologies, and 2 different communication technologies as well. Some communication technologies like CAPI and CXL going forward in Intel systems, for example, enable you to better offload computation to near memory engines. And that's what we did with these FPGAs. And we basically showed that you can gain significant performance and energy efficiency improvements on these two workloads. Again, we don't have time, but hopefully these give you examples that algorithm, architecture, device co-design can greatly improve performance and energy efficiency. And I believe we can get there step by step. So we talk about a lot more case studies in this paper, but let me now focus on some adoption issues. So clearly you can design hardware, but to enable the hardware, you really need to think the system issues. And essentially a lot of the issues on processing in memory boil down to the system and software. What are the applications? What are the software? How do we ease programming? What are the interfaces? What is the compiler and hardware support? How can we enable system and security support like coherence, synchronization, virtual memory, isolation, communication interfaces? How do we enable better runtime and compilation systems? How do we enable infrastructures to assess benefits and feasibility? I believe these are all very, very interesting research directions. There's a lot happening over here. All can be solved with a change of mindset. We really need to think data-centric, not processor-centric, to be able to solve these. Let me give you, but of course, in the end, we need to revisit the entire stack. So let me give you some examples. So I'll basically rush very quickly. There are many case studies on real applications, and we need more of these case studies, basically. You can see some of them are graph processing. Some of these we mentioned, graph mining, neural networks, weather modeling, time series analysis, approximate string matching, sequence to graph mapping, hybrid transactional analytical databases. So there are many, many applications that need to be, let's say, rethought with a data-centric paradigm in mind. Not just ignoring the compute-centric. I think we need to be heterogeneous in our systems. Compute-centric and data-centric need to coexist, let's say. And how do you keep it simple? I think this is important. Like processing, integrate into existing systems using simple instructions helps, for example. How do you maintain coherence? This is actually a very thorny issue. Existing coherence mechanisms do not work well, especially when you partition, for example, an in-memory database between CPU and near-memory engines. We showed that actually early on in 2016. So you really need better coherence mechanisms, and we designed some coherence mechanisms also. I believe there needs to be more work in this area. This is a thorny issue. How do you support synchronization is clearly important, and there's some work in this area. How do you support virtual memory is probably the hardest issue, in my opinion, because I think virtual memory actually needs to be rethought for existing systems, regardless of whether or not we go data-centric. Basically, even in processor-centric system, virtual memory is not scaling well. So in the remaining very few minutes, let me talk about processing in memory in the real world, because in the real world, this is already happening, basically. That's the upside today. Today, we have real systems. This is UpMem processing in memory engine. What they did was basically they have near memory processors next to each bank. And you can buy these modules by UpMem. We've been working with them. And we've been working with the system that has 2,560 DPUs. They call DRAM processing units, essentially a processing unit next to a bank. And you can see the simple processing unit over here. It's a von Neumann processor, let's say, and it increases the DRAM area, but people are building these today. It's a multi-threaded processor, basically. And if you're really interested, we've been writing papers about it. You can take a look at some of these papers. It's a shorter version of the paper. And we actually released some benchmarks that may be useful for the community. We encourage people to actually add to these benchmarks. These are all open source. And these are some talks that we have given that talk about the UpMem PIM engine. Okay, as I said, real systems exist where you can do near memory processing in FPGAs using HBM. One important issue in near memory processing is deciding which workload to, which part of an application to offload. And we developed some methodology actually to enable this more easily for the programmer. We analyzed more than 300 applications in this DAMU methodology. And we basically classify applications, classify functions based on their memory bottlenecks or compute bottlenecks. And these are 6 different categories. And by following our methodology, by using our methodology, you can actually classify every function this way. And these functions, this classification is a very good predictor of whether data-centric execution or compute-centric execution will provide you better performance. And this is already open source, both the methodology as well as the benchmark suite. So we'd be happy to help anyone who is working on this topic. And we need more tools like this to enable near memory processing, in my opinion, or processing in memory. And more recently, Samsung introduced their function in memory DRAM. It's specialized for neural network inference. Again, I will not bore you with the details. You can read their ISSCC paper as well as more recent papers. Basically, they can do multiply and accumulate operations near bank. Again, these are near memory architectures, and they have a very simple instruction set architecture, as you can see over here. And they've implemented it. They also collaborated with Facebook to design the system where you have a buffer chip on a module in this buffer chip, you can actually do recommendation, recommendation, essentially, accelerate recommendation, let's say. And this is another type of near memory processing engine. More recently this year, SK Hynix announced their accelerator in memory, where you can, again, it's designed mainly for machine learning, but they also target other applications like big data, computation, and storage, according to them, high performance computing. This is a more aggressive design, I would say, compared to the Samsung design. And it actually pushes a lot more changes inside the DRAM chip to add a near memory processing engine, and also copying support, data copying support, similar to what we discussed with RowClone, but maybe baby steps, let's say, compared to RowClone. And more recently, also, Alibaba announced their processing in memory recommendation system that changes the DRAM chip. So these are actually very, very interesting, in my opinion. Industry is moving forward with this direction, and hopefully they will continue to move forward. And hopefully we will see more hardware algorithm co-designs and software folks also picking up these systems and experimenting with them. So I think future is very, very interesting. We can enable new applications with this, in my opinion, and genome sequencing analysis is very interesting. Okay, so we're almost at the end. There's a lot more that I can talk about, but I don't have time, and we have a lot more information in our tutorials. If you're interested, you can check them out. Basically, if you want to be fundamentally energy efficient, we want to be data centric, and if you want to be fundamentally high performance, we want to be data centric. I can keep adding secure, robust, etc. I believe we want to be data centric over there also, but I think we have a lot of, let's say, evidence for being data centric, greatly improving energy efficiency and performance. And we want to minimize data mode, basically. So we don't have time for the next two parts, data driven and data aware architectures. And again, I'll refer you to this IEDM tutorial where we talk a lot about these things, or in our lectures. So let me conclude now. So I will argue that we today have to design systems that are truly balanced, high performance, energy efficient. We basically need to make our systems intelligent. And as I mentioned, this means, I believe, that we need to be data centric, data driven, data aware all at the same time. And an important part of this is that we need to enable computation capability inside and close to memory, as well as everywhere else in the system where we are not doing computation today. This can lead to orders of magnitude improvements. Hopefully, I've given you some examples, case studies over here. This can enable new application and computing platforms. We're working on them, and hopefully there will be even more examples into the future. Enable better understanding of nature, because nature is probably not processor-centric, and it has these three properties, at least these three properties that I mentioned over here: data-centric, data-aware, and data-driven, and who knows what else. And I believe future of truly memory-centric computing is bright, but we need to really do research and design across the computing stack in all communities. Okay, so we need to visit the entire stack, and we need to exploit good principles. And these are some principles that I covered in this talk that I will not mention, but I think more than anything else, we really need open minds across the research community as well as industry. I'll refer you to some of the papers, and I will acknowledge the funding that we have received. Thank you to all of our sponsors. Most importantly, I'll acknowledge my research group, whose work that I have mentioned in this keynote. And you can see some faces over here. And if you want to read more about our research, we have some newsletters. And everything that I've described, papers, talks, and artifacts, are available on these websites. And we open source our tools. You can find them also, and we'd be happy to get feedback. And we open source our lectures also. If people are interested in attending or learning more or contributing, they can attend our courses live on YouTube and participate, basically. And we have a specialized PIM course that I will mention that has been happening for multiple semesters now. And this is the current version that's still going on, where we cover a lot of issues in processing in memory. With that, thank you very much. And I'd be happy to take any questions at the moment.
Please, everyone, join me in thanking Onur for his great keynote. With this, let me now forward the attention to the audience. We have some time for questions. So if you have some, please turn on your camera and ask it. Maybe you can raise your hand in advance just so that I can coordinate. Alternatively, of course, you can just post your question in the chat. So Srinivas has a question, and for time being, he's the only one hope. So please go ahead. Turn on your mic.
Yeah. So am I audible?
Yes, you are.
Great, thanks. Great talk, Onur. And so one question I have is that can in-memory copy be extended to data partition in memory? As partitioning can actually be really useful for performance benefits.
Yeah, thank you, Srinivas. I think that's a great question, and I believe so. Although I have not seen a lot of work in that direction, I think this is a very good opportunity for future work that could use some of the primitives for data partitioning, for example. But I believe, yes, I don't see any reason why not, essentially.
Okay, great. Thanks. And second question, if I can.
Sure, go ahead, please.
Yeah. So also, do you see any opportunities for, say, in-bus computing, in the sense that wherein there's a bus between, for data transfer between memory and, compute?
Yeah, I think so, yes. I think it depends on what you mean in bus. So existing interconnects are becoming much more complicated. Clearly, we have a lot of hops, for example, and we have a lot of pipelining that also happens. So I believe, yes, there's opportunity for doing computation while the data is moving inside the pipeline, for example. And certainly if you have simple routers, you can add computation capability to those routers as well.
Okay. Yeah, thanks a lot.
Thank you so much.
So I had a
Maya,
question.
please go ahead.
Very interesting, and just so much material there. I was wondering what you thought about CXL, whether you think it has solved all the problems with coherence that you were mentioning, the research that you've previously done.
Yeah, so excellent question. Thank you, Maya. I believe it has not solved all the problems, but I think it's a step in the right direction, let's say, in the sense that at least the interface enables coherence. But what it has not solved is really outside of the interface, I should say. I think you really need also like better protocols or better designs that can reduce the coherence overheads by, let's say, minimizing the amount of coherence messages that you need to transfer. And that was our research on. I believe there needs to be more research in that direction. So I think that's kind of outside of CXL's domain. It could also be made inside of CXL domains, but I think CXL enables us to experiment with hopefully some of these coherence mechanisms. So that's why I think it's a good step in the right direction.
Yeah, that's a good point. I think that some of the round trip traffic for coherence has shown to be a kind of a bottleneck.
Any more questions from the audience? Thank you so much, Maya. Any other questions?
So I had I have lots of questions. It's a fascinating talk and so many topics that you've brought up. An impediment to processing near memory and DRAM has been, or in memory, has been the slower DRAM logic as opposed to regular logic. And I wondered what your thoughts were on how big a hurdle that is, or whether that is something that is circumventable.
Yeah, that's a great question again. So I think with the DRAM process today, that's very fundamental, right? It's not designed for logic. It's really designed for the capacitor density, essentially. So I think we probably are not going to be easily, let's say, designing 3 gigahertz processors near memory. We will hopefully gain out of the parallelism that we have across the processors. So I think in the same chip as that's designed with the DRAM process, it's going to be tough, in my opinion. But 3D stacking here, or monolithic 3D, enables us an opportunity. There you have different, let's say, processes that can be employed for the logic layer versus the DRAM. And you can put these things together. So I think 3D stacking enables us to overcome some of those issues. But of course, once 3D, it's not like being in the same chip. The data, you still move data over here. So I don't have a great answer for solving this inside the DRAM, unfortunately, except for taking advantage of the parallelism inside the DRAM.
If you allow me, I have a last question, but a really quick one, especially in terms of the ambit ideas, essentially in DRAM and/or computation. You stress the importance of the sense amps and how you utilize them. But when I talk to chip designers, they always keep telling me that sense amps really consume a lot of area. So how do you see this trade-off between speed of in-memory computation and area consumption for the sense amps, especially in terms of future memory technologies?
Yeah, so that's also a great question. Basically, so what we do with the ambit is we take advantage of the existing sense amplifiers in the sense that we don't actually increase the area cost. Of course, if you want to really make it robust, you may need to increase the area a little bit. So I think certainly adding more sense amplifiers to reduce latency, for example, will come at a cost if you actually choose to do that. I don't see any way out of that trade-off, because today, if you look at a sense amplifier, for example, the size of it is like 2 orders of magnitude larger than a DRAM cell, because the DRAM cell has been optimized a lot. So I think the solution should really, again, maybe the answer is similar to the earlier question. The solution is probably exploiting the massive parallelism that you have in DRAM, as opposed to adding a lot more sense amplifiers to reduce the latency of access. But I think this is what I kind of also mentioned with mindset. Maybe we need to shift our mindset from the very cost-driven mindset that we have in DRAM. That's kind of limiting our opportunities today. And I've talked to a lot of designers, DRAM designers also, about this. And they're in this mindset, let's say, that is very, very cost-driven. And if that's your only goal in life, you're not going to do anything other than what you're doing in DRAM design today. That's limiting innovation, in my opinion. But I think if we, let's say, relax the cost requirement just a little bit and increase the cost slightly, I think we can enable a lot more interesting DRAM architectures that people may be willing to pay for. That's the, yeah, that's my answer to this. Certainly in research, I think we should be doing that. In industry, we somehow need to break this, let's say, hugely cost-driven mindset in DRAM, because we don't have the same mindset. So if you think about the processors, we really don't have the same mindset on the processor domain, right? Accelerators, processors, we can keep adding stuff. Whereas in DRAM, we've kind of hold ourselves into this unfortunate, let's say, corner, and we're punishing ourselves in that corner, in my opinion.
Thank you so much, Onur. So everyone, please join me in thanking Maya and Onur for the very insightful and really inspiring talks. With this, I would like to close the session so that everyone can enjoy the short break. Have a nice day, and please continue enjoying HardBD-Active.